Hi, I'm Kemil and this is Chem with Chem. Now in this video we're going to be working the first 3 questions on the CSEC Chemistry Paper 2 for January 2021. We've already done questions 4, 5 and 6 in a previous video. You can just check out the card above for that one. So this is the other half to complement that one. So let's just get right into it. We're not going to spend too much time on this one. I want to do this one quickly, but we don't want to compromise value. So let us go. But just before we get into it, if this is your first time to the channel, I'm encouraging you to subscribe, leave a like, share the video, and also comment if you find value in this one. So thank you for joining again. So typical question one from CXC Chemistry. It's a data analysis question. So in this one, we're given a question as usual, worth 25 marks. So the concentration of a solution of sodium hydroxide in grams per dm cube was determined via the thermometric titration with a strong acid. The following procedure was used. All right, transfer 25 cm cube of sodium hydroxide solution that's of unknown concentration into a styrofoam cup. Take the initial temperature of the solution, then add 5 cm cube of sulfuric acid, and the concentration of the sulfuric acid. The concentration of the sulfuric acid is 0.1 moles per dm cube. So that big M right there is referring to molarity. So this was added from the burette into the cup. Immediately stir the mixture and record its temperature. So repeat procedure, adding 5 cm cube aliquots of sulfuric acid until a total of 30 cm cube of sulfuric acid is added. So this is a thermometric titration, right? So thermo means heat, so we're using heat change to actually determine when we've reached our end point. But the basic principle still remains that this is a titration. So we are using a solution whose concentration is known. So in this case, the standard solution is sulfuric acid. So we know its concentration, the concentration is given, so it's our standard solution. And then we're going to use the sulfuric acid to actually find the concentration of our sodium hydroxide, because a set volume of our sulfuric acid will react with a set volume of our sodium hydroxide. And there's a balance equation that actually governs how this reaction takes place. But just before we get into the calculation, the setup, this should be coming to your mind. We should be thinking about a styrofoam cup, and in the styrofoam cup would have added 25 cm cube of sodium hydroxide, and then we're going to, from the burette, release our standard solution. So we're adding 5 cm cubes each time, 5 mils, cm cube mils can be milliliters, can be used interchangeably. We're going to be adding 5 cm cubes aliquots, and we're going to record the temperature each time, or at least that's what was done. So we're asked now in this section to, we're asked in the, well, we're not asked anything as yet. So figure 1 shows the thermometer readings of the acid-base reactions after the addition of 5 cm cube, 15 cm cube, and 25 cm cube of sulfuric acid. So the first thing we want to do here, if we're going to take reading, we need to figure out what the scale is. So what each of these lines represents. So each of them represents 0.1 cm cube. So if that's the case, then it means that after we've added 5 cm cube of our acid, then it means that the temperature change is, what's that? 1, 2, that's 27, that's 27.5. So that's 27.5 degrees Celsius. After 15, this would be 31.1234, 30, well, after 15 cm cube, this would be 33.4 cm cube. And when 30 cm cube would have been added, then the temperature reading here is 28.9 degrees Celsius. So we're going to take these values and we're going to actually go forward with them. So here we will just fill in the values that we just got. So we just fill in our tables and we get the values for, we get marks for doing that. So we would fill in our 27.5, would fill in 33.4 and 28.9. So that's our table. And just for that, we've gotten 3 marks already. Yeah. Now, this is the section that we have to be extremely careful about. We have to be careful about everything. But here we're going to be plotting, and we're being awarded 4 marks for plotting. Now I'm just focusing on the graph, but you can just follow on your paper. Question 1B1 part 1 says we should use the axes provided in figure 2. This is supposed to be page 7. On page 7, and plot the graph of temperature against volume of acid added. So temperature is on our y-axis, volume of acid added is on our x-axis. So the same values that we just got, we're going to actually plot them. So before we start to plot, we have to figure out the scale. So if we look at the x-axis, we're seeing that each centimeter that is here is representing each centimeter that is here, each centimeter is representing 2 units. So we're going up by 2 each time, 2, 4, 6, 8, 10, and so on. And then on the y-axis, they've broken the graph. So we can break the graph to skip out parts of it that we will not be using. So we get our plot occupying most of the page. So in this case, they've broken the graph and we're starting at 20. And we're seeing that each centimeter here is representing 1 unit, 20, 21, 22, 23, and so on. So if that's the case, then it means that on our x-axis, each of these tiny, on the x-axis, each of these little stroke that we see that will represent 1 millimeter, each of them is representing 0.4 centimeters cube of the acid. And on the y-axis, each of the little ones that we see representing 0.2 degrees Celsius, just ensuring that we have a good understanding of what those tiny lines are representing, so it will make our plotting easier. So when we, just at the start, before we've added any sulfuric acid, when we've added 0 centimeters cube of sulfuric acid, our temperature is 25 degrees Celsius. Now, after we've added 5, and 5 would be in the middle right here. After we've added 5 centimeters cube, the temperature is 27.5 degrees. Temperature change, or the temperature reading, should say, is 27.5. After we've added 10, okay, but that's not 5, so we'll have to take that back. That's not 5. After we've added 5, the temperature reading is, so 5 would be in the middle right here. 5 would be halfway between 4 and 6. So 27.5 would be halfway between 27 and 28. So that would be just about here. And then after we've added 10, the temperature reading is 30.5. So 30.5 would be halfway between 30 and 31. All right, and then for 15, 33.4. So 15 would be halfway between 14 and 16, and the temperature reading there is 33.4. So we just have to focus a bit to ensure that we get it right. All right, and then 20, 32.5. 20, 32.5. This should be 20, 32.5 would be about here, halfway between 32 and 33. And we're seeing that the temperature is dropping now. Right. 25 25 would be between 24 and 26. And the temperature reading there is 28.9. 28.9 would be about here. So the temperature is going down. So it means that we would have reached our neutralization point. So any further adding of our 5 centimeters cube aliquots of the acid is now contributing to cooling down the system, because we would have already reached the maximum temperature, which tells us that we've come to our end point. So that was 25. So we know for 30, now for 30, the reading would be 26. 26 would be here. Now the next question, so that's the plot. The next question says we should draw two, so that's B2, 1B2. Draw two lines of best fit through the points on the graph. One where the temperature is increasing and the other where the temperature is decreasing. Now, lines of best fit should, they don't necessarily go through all the points, but in this case, they will go through all the points. So I'm going to use black in this case, or I'll continue with red. You'll be using your pencil in the exam. So this part gets a little tricky. I'm not using a ruler. I'm doing it on screen, but you'll be using your ruler to actually get your line straight. So let's see if we can do this free-handedly, just for the purpose of this video. All right, good. And I think I got it this time. Well, the first time. And then we're going to do the same thing. Don't know if that was beginner's luck. We're going to do the same thing for the temperature actually decreasing. And this feels a little awkward. So let's see if we can get this, get this, get this right. What you should have, which is to what we got earlier. And then this line now is what we would use to show the volume that corresponds with our endpoint. And then the reading there is 17 centimeters cube, and we're going to hold on to this value. This value is very important. So it means that when we would have added 17 centimeters cube of the acid, we would have reached our endpoint. That is very important because we're going to use this value now to help in our other calculations that are coming up. But just before we get into the calculations, the next question, part C, says we should distinguish between a strong acid and a weak acid. All right, and we know a strong acid is one that ionizes fully in water to produce or to liberate many H plus ions, or you could say it dissociates fully. Now, a weak acid, on the other hand, is one that partially dissociates or partially ionizes in water to produce few H plus ions. So part D, 1D, asks us to write a balanced equation for the reaction between sodium hydroxide and sulfuric acid. So we have the formulae, they're all there, they're all correct. So it's just a matter of balancing. And to balance, well, we're seeing that we have 2 sodium on the right, but we have 1 on the left. So we need a 2 in front of the NaOH. In doing that, we will get our hydrogen being 4 now because we have 2 from the sulfuric acid, 2 from the sodium hydroxide. So we would need a 2 in front of the water to fix that or to make that balance. Now the next question, part E, asks us to calculate the number of moles of sulfuric acid used in the reaction. And to actually do this, we're going to use a table. You can always ask for additional paper so you can do this working out. Right, so the purpose of this table is that it gives you a breakdown of everything that you have already for the question and everything that you will need. It gives you an idea of where you're going. So we have our standard solution, which is our sulfuric acid. We know its concentration, so it is our standard solution. We have the volume of it that was used, which is a 17 centimeters cube. We said we needed that from earlier. And then we have the mole ratio from the balanced chemical equation. We have the volume of the sodium hydroxide that was used, and the parts that are in green are the parts that we're interested in calculating. We know that that's where the questions are going to lead, but they're going to ask us this little by little. So in the first, they've just asked for the balanced equation, so we're now going to use the we're now going to use the concentration of the sulfuric acid that we have, that is 0.1 moles per dm cube. So the unit there for molar concentration is moles per dm cube. And we're going to use the volume of it that was used to find the number of moles that was used. So part E, we're calculating the number of moles of sulfuric acid used in the reaction. So 0.1 moles per dm cube what does that really mean? 0.1 moles per dm cube. It means that in 1000 cm cube, which is the same as 1 dm cube, 0.1 moles are present. So we would just put a statement to represent that. So we would say 1000 cm cube of our sulfuric acid solution contains, we could put an arrow or an equal sign, or we could say contain 0.1 moles. So it follows if we used 17 centimeters cube of this, if we sampled 17 centimeters cube, how many moles would be present? So what we're doing now, we're just solving for x. And then of course, we're not going to skip any steps. 1000 centimeters cube times x is equal to 17 cm cube times 0.1 moles. We're going to divide both sides by 1000 cm cube to make x the subject. And pretty much when we do this, I think division is commutative. When we divide the 17 cm cube by 1000 cm cube, we're in essence converting to dm cube right there. So this should give us, our answer right here should be 0.0017 moles. So that's the number of moles of sulfuric acid that would have been used. So now that we've found that, we're going to write it in. So we'll write it here, 0.0017 moles. So we've done that. So part F now is going to ask us to calculate the number of moles. So F is asking us to calculate the number of moles of NaOH in the 25 cm cube of solution used. All right, so then this is where we will look at the mole ratio. So the mole ratio of the acid to the base is 1 to 2. So it means that twice the number of moles of the acid is present in the volume of the base that was used, because it's a 2 to 1 mole ratio. Sodium hydroxide to sulfuric acid is a 2 to 1 mole ratio. So if 0.0017 moles was present in the 17 cm cube of the sulfuric acid that was used, it means that in that 25 cm cube of the base that was used, then 0.0017 moles times 2 would be present. So that would be 0.0017 times 2, which would be equal to 0.0034 moles. So there we are. Our table is now filling out nicely. So since we know that this value should be here, we could just go ahead and just put that value in. So we wanted to show how we arrived at it. So we've shown it, so we can just go ahead now and just punch that into our table. So our table is filling out nicely. So the only thing we're left with now is to find the concentration. And we look to the next question, that is G. G is asking us to calculate the concentration of the sodium hydroxide in moles per dm cube. So so In G, we're going to calculate the concentration of the sodium hydroxide in moles per dm cube. So here we are. We have volume of sodium hydroxide, and we have the number of moles that's present in it. So we can write a statement connecting number of moles of sodium hydroxide with the volume that we have. So that statement would say 25 cm cube of our sodium hydroxide contains 0.003 moles. And we know the concentration whenever we know the number of moles that's present in 1000 cm cube. So we would say 1000 cm cube of our sodium hydroxide contains X moles. Then of course, we're going to do the good old cross multiplication. So we'll get 25 cm cube times X is equal to 1000 cm cube times 0.0034 moles. All of this we'll have to divide by 25 cm cube to make X our subject, and we can just work this out, and this will end up with 40 times 0.0034. So this will give us 0.136. So the molar concentration of our sodium hydroxide is 0.136 moles per dm cube. So we'll put 0.136 moles per dm cube right there. And you know, there are persons who would want to use the formula here. They could have just said 0.0034 moles divided by 0.025 dm cube. That's just taking the 25 right here and dividing it by 1000 to convert it to dm cube, and we could just say molar concentration. Let's just get that up. We could say molar concentration, molarity is equal to moles over volume, but the volume must be in dm cube. So essentially, the cross multiplication, the writing of the statements is doing the same thing. And I prefer writing the statements. I would advocate for you, I advise that you write your statements, because under pressure you might just forget a formula. And the statement shows where you're coming from. You're more likely to get the marks by showing where you're coming from with your working. You make a mistake with a formula that you don't really understand, it probably will just, anyway, I think I'm over explaining here. This route is fine. So we've plugged that in. So we'll move to the next question. So our concentration, as we said, is 0.13 moles per 0.136 moles per dm cube. All right, so in part H, we're to calculate the concentration of sodium hydroxide in grams per dm cube, given the molar mass of sodium hydroxide being 40 grams per mole. So the molar concentration of the sodium hydroxide is 0.136 moles per dm cube. Now this could be written as 0.136 moles over 1 dm cube. So in converting this molar concentration to mass concentration, all we're doing here is converting the 0.136 moles that we have, we're converting it to grams. And to convert moles to grams, all we would need to do is just multiply by the molar mass. So the molar mass is 40 grams per mole. So we would just take the 40 grams per mole, which can be written as 40 grams over 1 mole. And of course, when we do this, we're seeing that mole cancels out mole, and then we'd be left with 0.136 over 1 dm cube times 40 grams. When we multiply that out, let's leave the units for the last part. When we multiply that out, we should end up with 5.44, and we're left with grams per dm cube, which is how we represent mass concentration. All right, so the next part, part I, state whether the reaction that took place in the styrofoam cup was exothermic or endothermic. Now we remembered from earlier on that the temperature increased once the acid was added to the base. The acid was added from the burette to the base in the cup, the temperature increased. So we know that this is an exothermic reaction. And we'll say it's exothermic because the temperature increased. So we'll say the temperature increased when sulfuric acid was added to sodium hydroxide solution. And then not only that, that's a neutralization reaction. Neutralization reactions are exothermic reactions. They release heat energy. All right. State one safety precaution, which should have been taken during this experiment. We're working with acids, we're working with bases here, so we would need to wear our personal protective equipment, such as goggles and gloves. One of the cool things about chemistry, we get to wear goggles. So we're at number two. That part took a little while. We don't want to spend more than 25 minutes on more than 30 minutes on number one. So in number two, R and S are two allotropes of carbon. R is a black opaque solid which can be described as flaky with a melting point of 3,925 degrees Celsius. S is a reflective colorless solid with a melting point of 3,823 degrees Celsius. Define the term allotrope. Now, allotrope, we'll just get right into it. So allotropes are different forms of the same element. Different forms of the same element, and we should be fine with that. Different forms of the same element with similar chemical properties. Don't want to over answer here. Different form of the same elements speaks to them having different physical properties. Identify the names of R and S. So once we hear black opaque solid, flaky, we should be thinking about graphite. So R would be graphite. And then, of course, S, reflective colorless solid, would be diamond. These are our two allotropes of carbon. Allotropes of carbon. We have other allotropes like fullerene, but we're looking at these two. These are very common, and these are what we look at this level. And then we have state whether R is an ionic, simple covalent, or giant covalent structure. Now, allotropes of carbon, we know that definitely graphite, diamond, we would have a giant covalent structure. And there we would have gotten 4 marks. In the space below, sketch the structure of R using solid lines to show strong bonds and dotted lines to show weak bonds. So we want to sketch the structure of graphite, and this is one of my favorite things to do. If you're not careful, you can just go on and on doing this. So we will have hexagonal rings of carbon atoms where each carbon atom is bonded to 3 more. And I'm not going to draw too many. We don't want to get carried away. And I'm probably getting carried away, so I'll stop right here. So that's one layer. We want to show that, so the solid lines are showing the very strong covalent bonds. So I'm drawing my second layer. 5. So there we have 2 layers. So we would now use our dotted lines to show the weak intermolecular forces of attraction that holds the layers together. And that is what causes them to be able to slide over each other, resulting in graphite being able to be used as a lubricant. So of course, I will give a little key right here to say that each of those little circles represents a carbon atom. Right, you could have drawn it using C and just connect just the same. So 3 marks. Part 5, explain why R conducts electricity, but S does not conduct electricity. Now R is graphite, so we have to go back to the structure. What happens in the structure? In graphite, we have each carbon atom is bonded to 3 others, and we know that carbon is tetravalent. So carbon has 4 electrons that can take part in bonding, but each carbon atom in graphite is bonded to 3 others. So it means that there is an extra electron that can now carry a current. So we'd have an extra electron for each carbon atom that would add to what we call the delocalized electrons, and they would now carry a current if a voltage were to be applied. So we're going to condense that somewhat. So we'll state that in graphite, each carbon atom is bonded to 3 others. So there's an electron from each that could carry a current. While in diamond, each carbon atom is bonded to 4 others. So in essence, we're saying all the carbon atoms in, all the electrons in the carbon atoms in diamond, they are being used. So there are no electrons, no free electrons to carry the current. Another solid T is white, with a melting point of 801 degrees Celsius. It conducts electricity when molten, but not in the solid state. Deduce the type of bonding present in solid T. So this bonding would definitely be ionic, and we should be thinking about sodium chloride here. And if you, I don't know which text you're using, but they have a nice table, I think, in the concise that gives a comparison between the structure of sodium chloride, diamond, and graphite. State the appearance that solid T is expected to have. So they said it was white in color. I mean, white could only be in color. So we would expect it to have a crystalline appearance. So we'd say crystalline. They said white already. We don't have to put back white. So we just state it's crystalline. Solids, liquids, and gases are easily converted from one state to another. Compare the arrangement of particles in solids with the arrangement of particles in liquids. So in solids, the particles are very close. So we're going to write in solids, the particles are very close. They're very close to each other, with very little space between them. We could say packed in a regular way. And then in liquids, the particles are packed in a less regular way than solids, with more spaces between them, for 2 marks. And then we have the last question from this number 2. When solid iodine is heated, a purple colored gas is observed. State the process which occurs and give one example of another compound which undergoes the same process. So we're getting solid changing directly to a gas, skipping the liquid state. We call that sublimation. And another substance that undergoes sublimation, dry ice. We could also use naphthalene. Many persons know this as camphor ball, NaPH, right? Naphthalene. All right, we just need one. We don't need to over answer. This takes us to number 3, and this is an organic chemistry question. 2-methylbutane and pentane are structural isomers with molecular formula C5H12. Define the term structural isomerism. So here we have a definition for 2 marks. So structural isomerism, we could say the existence, or we could just say organic compounds. Okay, let's try that again. Right, so whenever we have, okay, so we'll scratch that part. So whenever we have, whenever we're asked to define terms and we see ism at the end, then we know we could start by saying the existence, or we could say the existence, but we could just say structural isomerism, existence of organic compounds. So it's organic compounds with the same molecular formula, so that part is optional. Same molecular formula, but different structural formula, or we could say with different arrangement of the atoms in space. So here now we're supposed to draw the fully displayed structural formula of 2-methylbutane. 2-methylbutane. So the longest chain here will be 4 carbons. This is from the alkane series. It ends in ane. Bute means we're going to have 4 carbons in the principal or the longest chain. So we'll draw 1, 2, 3, 4. I like counting from left to right. So I'll call the carbon on the left carbon 1. And on carbon 2, I'm going to put a methyl group. So this is like giving an address, 2-methyl. But this is telling us that on carbon 2 is a methyl group. So I'm going to draw out the CH3 for the methyl group instead of condensing it as CH3. Then I'm going to just ensure that all my carbons are taking part in 4 bonds. So I'm putting on my hydrogens, and here this is a saturated molecule. All we have here are carbon-carbon single bonds and carbon-hydrogen single bonds. Not that carbon could have any other bond with hydrogen but a single bond. So the carbons, they have the maximum number of hydrogens attached to them. So we call this a saturated compound. So this is 2-methyl butane because on carbon 2, we have a methyl group. Methyl group is here, that's CH3 group, or could do it like this. That's our methyl group. So we should draw and name one other structural isomer of C5H12. Draw and name one other structural isomer of C5H12. Now, important thing to note, the word one is in all caps and other is bold. So we cannot use the isomer that we just drew above 2-methyl butane, and we cannot use pentane. So we'd have to use another structure. So what we could do to assist us, we could draw back the structure that we had a while ago. So I'm condensing it this time to save time. So we could draw that structure. And all we need to do to get another isomer is to find a way to cut and arrange this molecule so we get an arrangement that we never had before. So what I'm going to do, or what we could do, we could take the methyl group right here. We could cut off the methyl group that we have right here, and we could replace it with this hydrogen, or substitute, switch places. So we could put the hydrogen where the methyl is coming from and the methyl where the hydrogen was. And then when we do that, we would get another isomer. They ask us to draw it, and underneath it, we're going to give the name. So we're going to draw just that. So the longest chain would be, longest chain would have 3 carbons. And in the middle carbon, on the middle carbon, well, I'm not going to condense them. I'm drawing the fully displayed formula. And this has a little pattern to it. So the more you draw these compounds, the more therapeutic it should be. So here we have the longest chain being 3 carbons, whichever way you want to count it from. I like to count from left to right. So this is 1 for me, 2, 3. But I could use a different color. I could count, this could be 1, 2, 3. But either way, on carbon 2, there are 2 methyl groups. So how we would name this, we would say 2, and we use a comma to separate numbers. And because we have on carbon 2 a methyl group, so we're given the position of the methyl group. So there is one on carbon 2, there's another one on carbon 2. Then we use a dash to separate number from the letters. So we have to say that there are 2 methyl groups, so we would say dimethyl. And the longest chain is made up of 3 carbons from the alkane series, so it would be propane. 2,2-dimethyl propane. Part B, ethanol can undergo various reactions. Depending on the reagents and conditions of the reaction, products with different functional groups can be formed. What is the functional group of ethanol? And don't mind the lines that are there, you're just going to write the OH. That's the functional group. Or is it O? Right. So that's the OH group, and we will just move right along. Table 2 summarizes the conditions and products of 2 reactions of ethanol. Complete table 2 by inserting the reaction conditions and drawing the fully displayed structure of the products which would be formed. Take note that the type of product to be formed is given in the table. So here we're starting with ethanol, of course, and they want us to give the conditions that are required for ethanol to move from ethanol to an alkene. So the type of product is an alkene, would have to be specific and draw the actual fully displayed structure of the product that is formed. Now, to really do this, it's good to have an appreciation of what ethanol looks like. CH3, CH2, and I like putting on my OH group. I like to give it in red. It highlights it. So if we're going to get an alkene from this, well, we know that the first member of the alkene series has 2 carbons. So the only alkene that we could get from this is ethene. And essentially what we would have done right here, what I'm doing outside of the table, we don't necessarily need it, but I like to show where things are coming from. So what we've pretty much done here would have removed water. So it means that the conditions necessary would be those that represent a dehydration reaction. So in this case, we would need concentrated sulfuric acid. We would need 170 degrees Celsius. Concentrated sulfuric acid is a dehydrating agent, or we could pass the ethanol vapor over aluminum oxide and heat this to 450 degrees Celsius. Either of the two would be fine. This time around, we are using CH3COOH, that's ethanoic acid, and they're saying that the product that is formed is an ester. Of course, when alcohols react with acids, we end up with what we call esters. That's another class of organic compounds. So the reagent, the conditions that we would need heat, we would need acid catalyst like sulfuric acid as catalyst, and this takes place under reflux. Many books won't give this, but this takes place under reflux. And the ester that we would, so just a reminder what our ethanol looks like. So this is what the ethanol looks like. And this one will be a little easy because our alcohol has 2 carbons, our organic acid has 2 carbons as well. But anyway, when we're drawing the ester, we normally draw the acid part first. So what will happen, we're going to have the OH. So all that I'm doing over here is just explanation. So we'll have the OH. So let us look at how this reaction actually takes place. I'm going to turn this molecule around. I'm going to flip the ethanoic acid, CH3, C, well, I'm going to redraw it, CO, and then we'll have OH. So I'm going to show how they're joined, and then we just go ahead and show what the ester would look like. Don't need to show all of this, but I just want to explain how we're arriving at the ester. So it is the OH from the acid. It's the OH. Okay, I've lost my H right here. So it's the OH from the acid and the H from the alcohol. And this would come off as water. But the final product, when given the final product, we would draw the acid part first. So this is the acid portion, and this is our alcohol. So we'll draw the acid part first. So I'll just keep the color, I'll be consistent so we can see the acid portion. So we'd have a CH3, then we'd have a C, double bond O, and then we would have the O from the alcohol, and we'll be consistent. Then we'd have a CH2, then a CH3. And we're going to, of course, dress it up, put on the hydrogens where they're supposed to go, and that is it. They did not ask us to name it, so we'll just move on. We'll just leave it here. And this is pretty much it for the first 3 questions. The first half of the CSEC Chemistry Paper 2 for January 2021. Again, I'm encouraging you to subscribe to the channel if you have not done so. Share the video with a friend, someone you think would find value in it, and also like and leave a comment. So thank you for joining us, and couple later.